today to interact with you about the force gravity, which is sort of big and easy to understand, and the history continues from past, I don't know, from the beginning of the man. I'm going to tell you how, but officially you can consider it as around 400 or 400 plus years. So since 400 plus years we have been studying gravity, but still we don't understand gravity to 100%. But we understand it better than any other force, as I said before. So I'm going to start off with, when did we first saw the sky? I mean, everyone here are amateur astronomers, or at least you're starting off. How did you feel when you just looked at the sky in a different way, in a different attitude and atmosphere here? It would be so bone-chilling, right? And the same feeling would have, they would have experienced. The first people who saw the sky, they would have seen tiny lights. They didn't know what star was or a planet was. Those lights would move from east to west every day, and they didn't even have the sense of direction at that point of time, and all this. So this was the first time, and I can track back as back as the times of Aristotle. These were the first times when people saw the sky and they said, okay, there is some pattern in the sky probably, or these dots are moving from east to west, and quite literally, to be honest, I was in November, in Himalayas in November. I was doing some experiment related to cosmic rays, and it was about 1 AM in the night, and my experiment, something went wrong with it, I couldn't fix it, so I had nothing else to look up, nothing else but to look up at the sky. So when I stared at the sky from 1 AM till sunrise, because we were isolated like about 2 kilometers from Kilo, so you had no, I didn't even find a human being. So at that point of time, every star actually moved from there till here, and every pattern in the sky, rise and set. And I used to wonder, am I at the center and everything is moving around me? For a person who doesn't, even have the capacity to think that the ground that I'm standing on is actually rotating and revoluting around a big ball of fire for now. And it takes such and such time to rotate, and it is periodically repeating from millions of years or even billions of years. So it's something that's way beyond the first people who saw the sky, right? So, generally, first theory that one proposed was the geocentric theory. Geocentric theory, the name itself suggests that the Earth-centered theory. So the people, initially, they thought the Earth was at the center of the universe. Mind you, when I say universe, only the visible dots in the sky represent the universe, not the universe that Hubble Space Telescope has discovered. Okay? So this was the universe to begin with. And people said, okay, the Earth is at the center and everything moves around. And you can expect church and people who are very religious to say, Earth is very holy and land of Earth is holy. There are a lot of people who are something way beyond, close to God and all those concepts. Anyway, that came in. So Ptolemy was the first person to propose, in a more scientific way. People had this basic idea, that okay, probably the Earth is flat, everything is moving around here. But Ptolemy proposed it in a more scientific sense. Okay, that's why the foundation was laid so hard, that it took probably lives of many people, many scientists, to actually come out of it and say that okay, the sun is at the center and everything moves around here. Planets, not the universe. So geocentric theory was the first theory that they proposed. Later on, Galileo was the next person who actually opposed this, and that's why he was killed by the church. And they don't call it as killing, they call it something else. Since I'm not a religious person, I don't know what the exact term is. So that's one. So Galileo was one of the first persons in the history of mankind, if I can say, who studied the nature closer than anyone else. He was the first person to study the nature around him. He experimented with balls, rolling from an inclined plane, and he introduced a term called as change in velocity. Okay. If you are versed with calculus, you will know when we calculate the acceleration, we And in the numerator you have change in velocity, you have some equation to do. Anyway, complex stuff. So change in velocity was introduced by Galileo for the first time. Galileo introduced inertia. The law of inertia was actually postulated, it was proved by Galileo, to be honest. It says if you roll a ball, the ball actually rolls infinitely long and forever until and unless something opposes it. So inertia. And later Newton actually was a big fan of Galileo. Newton came up with laws of motion, everyone knows. The first law of Newton is nothing but the law of inertia itself. And the second law is that relates the force to the acceleration. So Galileo had already had a sense of acceleration, but he didn't know. Probably if he was alive, he would have proposed all the Newton's laws of motion. But thanks to the church people who killed him, he didn't. So Newton, with thorough analysis in Cambridge University, he used to lock himself in a room for 13 hours a day and he used to work. And because of that working and all those experiments in the lab, he found out this equation. F is equal to m. I'm just going to explain how it works. The force is proportional to acceleration, which means that say I give x newtons of force to an object, it moves proportionally. The acceleration of the ball or any object will be proportional to the force that I provide. Okay? And it's the same thing in nature wherever you go. So this was one of the basic laws, but the discussion that I want to make today is gravity. So gravity, everyone knows. Newton is the guy who's behind gravity. Newton's law of gravitation is considered to be the greatest, achievement of a human mind, of all time, because it is one of the basic forces, and we understood gravity to greater extent because of that. And the equation that Newton produced is F proportional to m1 or m prime r squared. Let me explain. F again is a force, gravitational force in this case. The gravitational force varies according to this equation. Force actually increases if you have two big masses. But don't ask me what happens if two fat people are sitting and is there any gravitational force? Yes, there is gravitational force, but it's very weak, and that's the reason why it's weak. Again, we'll come back to that later. So gravity increases if there are any two celestial objects. If they have a lot of mass, there is a lot of attraction between them, and this is the reason why the Earth moves around the Sun and not the other way. Okay, and this is the distance between any two objects. Okay, if the distances increase, the gravitational force tend to decrease, and this is what the equation actually says. So, who actually told that the Sun was at the center and everything was going around it? It's a question anybody can answer. Copernicus. He was a son of a blacksmith, I believe, and he worked so hard in bringing his theory or Galileo's work into light with a lot of mathematical equations and proofs. When Ptolemy proposed the theory, he said all the objects that move around the Earth are in circular orbits. Okay, orbits was defined very well. He said the planets move around in circles. And of course, the same thing was adopted by Copernicus, and he said that the Sun was at the center and everything moved around it. Sun was heavy. So this was one beautiful illustration of how things work. Later, after Newton proposed this theory of gravity, there was one question to Newton that he didn't answer, and we didn't find the answer, to be honest, for probably 300 years after Newton. That was why gravity is an attractive force. Let me tell you some stories behind it. Newton one day was sitting in his estate under an apple tree, and see, when I was in school, middle school, we used to play a game. Whenever our teachers used to come and teach us, they used to scold certain students that you have an empty mind, you don't have anything in your brain. Okay, and we are very young, we don't understand that he was behaving foolish. We actually thought there could be a thing in the brain. So we used to test it. How do you test it? You knock people's brain, head. You knock people's head, and you test it. If the sound that comes out of the head is more in terms of amplitude, then that means that the guy's brain is empty. Empty vessels make more noise. Yeah. So the same way, actually there was a guy who thought of testing Newton's head, okay, whether it had something or not. What he actually did was he threw a stone to the apple. I mean, he wanted the stone to hit Newton's head, but it missed and it hit apple tree, and the apple fell on Newton's head. And Eureka! Newton thought, why should the apple fall down to the earth? And then came up the universal law of gravity, which said any two objects in the universe will have a force of attraction towards each other, which varies according to the formula that I wrote before. Okay? So this was one of the great movements in the field of physics. Right. Now the question was, why if there is force of attraction, why does the earth move around the sun in circular orbits? How does the force work? And why is the motion in the way it is? Then Tycho Brahe was a man who actually was working with Johannes Kepler. And Tycho Brahe, he was a very rich man. He owned an island near Copenhagen. And what he did was, since he was rich, he could afford to fit grass caps all over his islands with respect to the positions of the planets. Galileo, remember, had already discovered moons of Jupiter and rings of Saturn.
What did you say?
Grass caps, which had a small hole, through which you can see the position of the planet. You could record, I don't know what sort of measurement techniques he had, but he had done the measurements. The most precise measurements actually came from Tycho Brahe, even though there were not much technology compared to today, right? So that those ideas were given, those whatever the calculations that Tycho Brahe made were given to Johannes Kepler. Then people realized that the planets are not moving around the sun in circular orbits but in elliptical orbits. And this was the first law of Kepler, wherein he says, planets move around the sun in ellipses. Okay? So I'm going to draw, but I'm not good at drawing, so excuse me. Okay? So the orbit, probably you all know, is in the shape of an egg. So, say this is the sun at the center and this is Earth. Probably I'm going to let me remove this foci. So what the next law was more of a mathematical law, because there were some errors. Kepler thought there were errors in the observation that Tycho Brahe made. Okay? There was some deviation in the orbits. That's the reason why he concluded that the orbit was elliptical rather than circular. Okay? And it looks somewhat like this. It looks like a potato. No? However, the next law is something with respect to the areas. So if I take this area with two positions of a planet, say about 3 weeks, here 3 weeks and again somewhere far away from sun. Again, this is also 3 weeks. The area here covered by the planet and the area here will be the same. Okay? Which means apparently Earth should move faster when it is closer to the sun, and the Earth should move slower when it is far away from the sun. That's why winters are long and summers are short. If you can take it. So the planets will cover equal areas and equal intervals of time. So that is the Kepler's second law. Okay, equal areas. So the next law took a long time because it is completely mathematical. And of course, it came from the observations. So it relates the size of the orbit and the time taken by the planet to cover that size. Okay? So it is as such as T proportional to A to the power of 3 by 2. Okay? So the square of the time period that taken by the planets is directly proportional to the cube of the areas where the size of the orbit, you can take it as the longest distance in the ellipse. That can be the size of the orbit. So this was one of those extraordinary discoveries, and the first time someone could say, okay, we understand solar system precisely, and because of these laws, we could be able to predict more planets, exoplanets, more precisely. And again, when you point out the telescope at that particular position, you can find new planets. Okay, so people still use these laws. It's universally correct and applicable. So the next that I'm going to talk about is, it took a long time for people to come up with. For a long time people thought, I've still not answered your question, why the earth rotates around the sun. Yes, there is a force of attraction. If the force of attraction is between the two planets, then say between probably the sun, then if this is the earth and this is the sun, if there is a force of attraction between the sun and the earth, they should collide. They are not colliding. Me and you are alive, and they are experiencing one of the best seats in cosmic theaters, actually, to be honest. We are looking at the cosmos and we are experiencing life which is everywhere around us. And so, if we were closer to the sun, probably, the Goldilocks zone, right? Where the life is habitable. If we were away from the sun a little bit, probably life would have frozen away. If we were a little bit closer to the sun, probably life wouldn't exist, right? So, it doesn't happen. Earth moves around the sun in an elliptical orbit, right? And why? And what's the reason? There was one school of thought who said that there were angels who actually flapped their wings in such a way that they powered the planet's motion. They didn't understand that there was some sort of a force called a centripetal force, which actually was the reason. And there is a centrifugal force. Both balances, and hence you get a shape as such as this, right? So the angels had to flap their wings. Actually, to be honest, when Newton was giving out all these theories, publishing these theories, there were a lot of people who were dying. So you can see a lot of people dying, so a lot of angels in the heavens. So there are a lot of angels in the heavens, so that's the reason why a lot of, the earth could move faster around the sun. But the problem comes in this position, somewhere here. Like angels could manage to power the earth ahead, right? But at this point, you need to turn, right? The orbit is not straight. You need to turn. What the angels had to do was, they had to flap their wings at an angle so that the earth moved in those particular direction. So this is one important point that I needed to make. Because I can tell you how exactly it works, but as I said, the centrifugal force and the centrifugal force balances, and that's why you get an orbit that is parabolic. Right? So the next thing was, F is proportional to m prime by r squared. When I said there is two bodies, okay, irrespective of where it is, right, or what it is, but this is the r, the distance, and this is the mass of this object, and this is the mass of the other object. But Newton gave this formula. Newton knew, there was a constant. If you want to write it in the equation form, like some constant here, say k times m prime by r squared. We all know it is the universal gravitational constant, but Newton did know. And a lot of people don't credit this guy called as Henry Cavendish. Okay, Cavendish was a great man. Of course, he was not popular like Newton or Einstein or anyone in the field of physics, because the experiment he did was so complex, people don't even bother to touch the book. It's called as Cavendish experiment. He accidentally found out the universal gravitational constant. He was actually trying to find out the density of the earth. He was one of the person who was working in the Royal Society of England, but he was an odd kind of a guy who never spoke to anyone. He used to walk from his home to the Royal Society or his lab, wherever it was, in the same path, every single day. How much ever years he worked there, every single day he used to walk in the same path, never used to talk with anyone. And there is little known about this guy, Henry Cavendish. But he did such an experiment that not even Newton could think of. Okay? I cannot explain the experiment, it will take too much time. You can refer to a book published by Prism and Pendle. You will find finding the density of the earth. It's a very good experiment. You can actually get it. If you have time, you can read it. So he found out in a lab, he fixed two masses just like this, suspended with some sort of a cord, this special quartz cord, which is made of quartz. So he actually measured the gravitational force between the two objects Even if it is Himalayas, if I take the Himalayas and put it next here, there will not be enough gravitational force to attract me. Right? The gravitational force is so weak, and he had to measure the gravitational force between two objects which is roughly about this size. And you could understand how precisely he had to conduct the experiment, and he had to be so patient about how the light deviated when the experiment was conducted. So you can read it, experience the movement on your own. It will be a nice one. So this was, Cavendish was the person who actually gave or calculated the universal gravitational constant to be 6.610 power minus 11 Newton meter cube as kg square. Correct. Right? So this was found out by Henry Cavendish. And it was, now it makes sense. Before I had to tell you only this, that if the masses are large, there will be a lot of gravitational force. But I couldn't tell you the exact precise magnitude, right? No. But this gravitational constant that was actually identified by Einstein, believe it or not. Einstein actually recognized this constant. He said it can be applied everywhere in this universe. Cavendish is a shy guy. He didn't even bother publishing, to be honest. And the history is so. So this actually gives some magnitude if you apply it. G(m) prime by r squared. This actually completes Newton's law of gravity. Okay, it is the greatest generalization achieved by a human mind. So something to be proud of ourselves, since we have inhabited this planet. It's the first time actually we have concluded or come across a force and we have understood it to the fullest. Now, this is about the classical part that I wanted to explain. I'll move to the more modern part. Obviously, it's 100 plus years. Still, people, when they write the textbooks, they follow the same thing, the modern physics. I really don't understand what's modern about it. But anyway, modern physics is what I'm going to start off. Now, during the times of Einstein, there was only two known forces. Okay, the fundamental forces. There were a lot of forces that you mentioned, but the fundamental forces were electromagnetism and gravity. And since we understand gravity, we actually, I can say only this was properly known. But electromagnetism was understood to a greater extent thanks to the works of Michael Faraday and Maxwell. Faraday actually was the guy, was interested in physics, was oystered, conducted experiments, and later actually found out this magnetic field that when you pass an electric current through a conductor, it actually produces a magnetic field around it. Discovered by Faraday. He is the father of electricity, right? Later, Maxwell, one of his pet students, if I have to say, Maxwell was guided by Faraday throughout. At least till he proposed the electromagnetic equations. Faraday actually helped Maxwell with his equation. Faraday's mind setting was in terms of pictures. Faraday thought in terms of pictures. Maxwell thought in terms of equations. It is a dangerous combination in physics. When you add both, you get a great theory that stands to the test of time. Newton had a very great mathematical background, but he didn't have this picturizing ability that Einstein had. And because Einstein's and Newton's theory of gravity bring it together, that explains gravity to a greater extent and a clearer extent than any other theory, right? If you take individually, there is some buts and ifs and something like that. So we don't understand that. So Maxwell and Faraday was again one of those contributions that we have to remember throughout history. So however, actually Einstein was interested in this gravity, and relativity is full of gravity. Relativity is one piece of document that explains the universe in bigger size. If I take electromagnetism, which is, let me say, electromagnetism is unification of electricity and magnetism. Okay? unification of these two forces. That means it just united. And Maxwell did it mathematically. Faraday did it in terms of pitches. Okay? Maxwell said, how does a light propagate? So there is this, some sort of a node that people write when they represent a wave, right? So this is say a light beam, and I'm just taking part of a light beam, one wavelength probably. This is an electric wave, electric field, and this is a magnetic field. They are at mutually perpendicular angles, right? This is basics of physics, basics of electricity. But what Maxwell proved mathematically, this was told by Faraday actually. What Maxwell proved, that this electric field produces magnetic field. This magnetic field in turn produces electric field. This electric field produces magnetic field. Up to infinity, wherever the light ray touches, this is the way light propagates. Okay, light doesn't, it's not being pushed by anyone with a force to go somewhere, right? Photon, you go there, you want some light. No, it doesn't work. The light propagates in this way. Electric field producing magnetic field. Mutually, they produce each other, and that's how light propagates through vacuum. And there was this, concept of ether that I'm not going to mention again. I'm just going to skip that bit to relativity. Einstein's Relativity was the most famous publication of all time. People say so because when Einstein, when it was actually, the experiments were conducted, yes, it was famous. But when Einstein proposed the theory at the age of 19, nobody even bothered to look at the theory or the paper that he published. Right? And Maxwell was the first person, not Maxwell, Max Planck was the first person to actually identify Einstein's work, because Max Planck was working on the same lines. And this guy, who was a student of some polytechnic school in Berlin, had come up with this beautiful theory. And he was thrown out of the school and he was working in a patent office that he didn't know, however. So, he identified Einstein, and the rest is history. So, Einstein's theory of gravity works in this way. I'm going to explain it to you, because when you look through the telescope next time, when you look at big stars such as Betelgeuse, which is a red giant, it actually, let me come to the basics first. So if there is a planet or a star such as this in space, nobody can see anything. Space is dark. There is nothing in space, right? You're wrong. However, there is electric fields and magnetic fields that I'm not going to take up now. However, space is not empty. And space is another dimension. Everyone knows the 3 dimensions, right? Thanks to the 3D movies, these days physicists don't have to spend much time explaining how 3 dimensions work. So this is the way we represent 3 dimensions. Okay, X, Y, and Z coordinates. This is the 3D world. The length, the height, and the width. Now I'm going to introduce you to one more dimension called as time. This is the representation of 4 dimensions on a 2-dimensional plane, which I agree is wrong. You cannot represent it in this way. But however, I'm going to explain. Time controls the 3 dimensions, which means that the 3 dimensions are embedded in the 4th dimension, which is higher dimension. So whatever happens in 3 dimensions is controlled by time, and everyone knows this, right? So time, you can imagine it as a cloth, piece of cloth, stretched at all ends, okay? And if you place balls, which is supposed to be celestial objects, there is some depression that's created on the cloth, right? All have experienced this. The same thing happens in space, and that's called as space-time. And the curvature looks something like this, okay? So this is sun. Sun actually curves the space-time around it, okay? And this was the prediction of Albert Einstein, which took a long time for the astronomers to prove. So there you understand what's the relation between a theoretical physicist and an astronomer. Without each other, it doesn't make any sense, to be honest. We need both astronomy and theoretical physics. So here, Albert Einstein mathematically proved that there is a fabric of space. We call it as space-time or space fabric. Again, just like the fabric, cloth fabric. Can you imagine? So the same way the fibers in the fabric that you use, the cloth, fibers in the cloth expand if you place a heavy object on it. The same way the space-time also stretches. Okay? And again, it curves also. So what happens at this point is that the gravitational force, which Newton said is due to the gravitational pull of the earth. Newton said apple is falling towards the earth because the earth is pulling on everything, right? Well, it is not so. Albert Einstein actually proposed this theory, and if he was not supported by Max Planck, his theory would have been thrown into dustbins. Nobody would have gone against the great Isaac Newton. Okay? So, but Max Planck was backing him up. So now I am going to introduce Earth in this picture. It will make some sense to you as soon as you see the Earth. Earth is rotating around the Sun. The reason why it's rotating around the Sun is because of this curvature that's created by the Sun. Right? The curvature is very small, it's not even 1 degree. The Sun is so big, it's a big ball of gases. Even though it is that big and huge in the sky and also in the real sense, it creates, the curvature, angle of curvature we call is 0.7 arc seconds. And somewhere around 0.7 arc seconds. How small is it? And how was it proved? There are many stars even behind Sun that we cannot see. Right? Sun blocks it during the daytime. What people did was during the total solar eclipses, you can see the other stars, right? There's a window of opportunity during every total solar eclipse, wherein you can see that the star's light is bent. And people introduced one of the greatest astronomers of that time, working at California Observatory. He actually traveled all around the world while proving this great patent clerks theory. So he actually, many attempts were made out of probably 7 or 8 over a period of say 30 long years. I can precisely remember, at least 25 years. Because of the war and all, it was postponed and so many other stuff that happened. They proved with the photographic evidence that there is curvature, and because of this curvature, the light ray from those stars actually bends. Okay, so the photons bend because of this curvature. There's not much, as I said, the curvature is not much, so the bending is not much. But if you can take quasars, which are huge, then the light that is bending from the quasar is awesome to see. It creates something called as gravitational lensing. It is better you Google it and see the pictures of gravitational lensing. You get lensing images. It's so wonderful. Okay. Actually, say there is a quasar here somewhere behind it. Sorry over there. Quasars are huge. Their mass will be about 5 billion or 6 billion times the mass of the Sun. Okay, and they're distant also. None of the quasars are closer. The minimum distance, if I can remember, is about 5,000 light years from Earth. So if there is light that is coming from the quasar, we can see that the light actually bends around the star. Need not be Sun. If I am observing somewhere from here and I have my telescope here, right? My telescope assembly. If I see the light ray actually bends and I see 2 quasars here, mirror images of each other. And when you take a picture of it, in one picture, actually, if I can ignore this bit, you will see 2 quasars, mirror image. And this happens because of bending of light. And Albert Einstein proved it, but nobody was ready to believe it, and hence he didn't get the Nobel Prize for this, which he deserves to get the Nobel Prize for this. But he didn't. So this is something that is great all time. You can see the effect of gravity, right? So now, is gravitational force a pull or a push? In first grade, we have all learned force is push or pull, right? To be honest, there is nothing but the pull there. Because if I have to slap someone, I actually push him, right? I push his cheeks. That's why he gets the reactions, whatever he gets later. But nobody pulls him from the other side, and you cannot expect the same reactions, right? So force is always a push, and I'm going to explain how that push works here. I drop this pen, the pen will come down, not because of the attraction of Earth on this pen. It's because of the fabric of space that is invisible to us is pushing on everything. And even on this pen, and even on me, and even on every one of you, and every speck of dust in this room. And that's the reason why everything stays closer to the Earth. And of course it depends on the curvature that created by the earth. And 4 dimensions, you can imagine 4, not 3D world. So there is this blanket which is invisible, that's pushing on everywhere, every one of us. And that's why we are on the ground. And also you, it's part of your disaster to run out. It is the way it is. And thankfully to gravity you are all sitting in your chairs. Right? Now, I think this is about what if the star here is big enough, very big enough, and the same quasar is here, there will be light from all directions, even from the top and the bottom. What this actually creates is something special, a phenomenon known as Einstein's rings. Okay? Einstein ring is what I said, the way you get a mirror image. You get a 360 image of quasar. Okay? 360 degrees, you get an image of the quasar. So this is rarely done thanks to the softwares where you can edit the photos and all. People do a lot of stuff and put it on online, but it's a very rare event. You can check out how Einstein's ring formed. It's a very beautiful experience if one can find. And probably in the telescope observatory in Arizona or somewhere, people have taken a picture of Einstein's rings, which I recently saw. Okay, now let me go to the smaller stuff, which I am working on. Quantum theory of gravity. Now, as I mentioned, there are 4 basic forces in nature: the strong, the weak, the electromagnetism, and gravity. Using these 4 forces, we can define every other force in nature, every other force one experiences. Right. So, strong force is existing between the nucleons. Nucleus is together because of the strong force. The short range force. Beyond the nucleus it doesn't work. Okay? And weak nuclear force is the 3rd strongest force in nature. Not written according to their force, range of their force. Written according to the ranges of their force, not in terms of their strength. But the first strong force is the strongest force in nature. The electromagnetism is the 2nd strongest force in nature. So the electromagnetism, what it does, it keeps the electrons around the nucleus, and it is present in stable atoms. The atom is stable because of this electromagnetic force. Okay? And the weak force is present in radioactive elements. Wherever, if you take a radioactive element, you never know what particle pops out of the radioactive element. So, it is weak. And the electrons also pop out. So, there is no definite orbits for the electrons. For time being, you can place an electron in an orbit and do whatever calculations you can. But you have no guarantee that the electron will stay in that same place. Or at least in the same orbit. So, that's the reason why it is. And the gravity, I've explained it, so that's good. So every one of these forces have their own particles. Every force has a nominated particle. Like every company's got a nominated person who deals with all those external affairs. Just like we have in our government external affairs ministers. So the same way, the external affairs particles are always present in all these kind of forces. I'm interested in gravity. Since we don't know what particle is responsible for gravity, we have named it as graviton. The energy needed to discover this particle is immense. Even in LHC, you cannot produce such energies to actually, pop out this graviton. You can actually, they have discovered Higgs boson, but it is immensely difficult to actually see the graviton in action, right? So electromagnetism is responsible is the photon, and then I represent it with gamma rays. Gamma rays is photons, it is same. So gamma or photons, what they actually do? Actually, there is some sort of interaction that we don't know. We call it as a virtual photon. What exactly happens when there is a proton and an electron? This photon actually interacts between the two. And that's the reason why this proton knows, let me write it as plus and minus. this proton knows that there is an electron and I need to attract it to this. In the same way around, electron knows that there is a proton. How? Oh, you might say there is some force, the field around the proton and electron. Yeah, fine. But still, how does it work in quantum physics? There is a virtual photon that is smashing between the two and letting each other know that, hey buddy, you are positive, and that there is one guy at certain distance is negative. You got to attract to him, and if you come too closer, then you lose your charges and you become a neutron. So this, the photon is called as an information carrier. The virtual photon is called as an information carrier. That's the way electromagnetic force works in the atoms. Alright, so how about graviton? But this is a very childish explanation. So there is Earth, there is Sun. How does Sun know that there is Earth? And why should they attract? If I apply the same principles, how should they attract? Let me tell you some properties of gravitons. Even though we haven't seen it, there is mathematics always to tamper with, right? So before, let me go back some years. There were two groups, called as physicists and mathematicians. Okay? And they used to work separately. I mean, in a sense, they always produced one result that helped each other. Mathematics, you write equations, if you don't know the physics behind the mathematics, you don't understand mathematics. And you write equations in physics, if you don't know mathematics, you don't understand physics. It's a simple rule. Nature speaks in mathematics, and you are trying to study nature, which is physics, and you don't know mathematics, that means you don't understand either, right? But today, what physicists have done, since the birth of quantum physics in 1920, a lot of people started learning mathematics also, okay? So these days, physicists themselves know how to create a situation in physics, custom made, that it fits into their theories. That's the reason why, after 1960, there are more than 1 million papers alone in string theory that explains how the universe was formed, how it is going to die, and all the stuff A to Z about the universe. There are 1 million plus papers. For a student like me, which should I refer to? And will I refer to all the papers in my lifetime? No, it's not possible. It takes a long time to study one paper at a time, right? Okay, what about this theory? Is it the same way? Well, no. There are some things that are worse with physics in graviton. For example, it is massless, there is 0 kgs. Okay, it doesn't have any mass. That means the mass of the sun is not because of graviton. Okay, whatever we have understood before, that the mass comes from the matter, right? With matter there is this intrinsic property that comes called as mass. You don't have perfect definition for mass also. So, now what happens with the earth and the sun? Take first half of the sun, first half of the earth. This is my way of explaining it. And again, I told about the Newton, the stone throwing, that bit is my, I thought you would laugh. I don't know why you didn't. Anyway, here is gravitons all around it. Particles, billions and billions. Okay, the first half of the sun is looking at the first half of the earth and it says, oh, there is this guy, he's got some mass, I got to attract to him. There is some attraction. And it depends on number of gravitons at the surface. Okay? There is some mathematical bit and scientific sense to this, but in the easiest terms, there are gravitons that are surrounding the sun's surface, all over the sun's surface, and all over the earth's surface. Everything that exists in the universe is surrounded by graviton. Right? So the graviton sees it and says, okay, it's got to attract. Because my aim in life, if you talk about philosophy at this point of time, people say where science ends, philosophy starts. Rubbish. However, here, where these gravitons look at each other and they say we have to attract because it's our destiny. So that, in one sense, they create bonds. Okay, long-range bonds. Graviton or gravity as a force, even according to mathematics that was done by Newton and Einstein. For example, if you take the sun, right? You have 9 planets, you have Kuiper belt, you have Oort cloud and whatever in the solar system. And whatever is included is part of the solar system. And it stretches up to 9.1 trillion miles. and we call it as heliosphere. And this is some mean value. Okay? But in every direction, sun's influence can be felt even after you travel away from the sun up to 9.1 trillion miles. Okay? So when you travel such a long distance, what happens then? Is a question. What will happen to the gravitons? They will be long-sighted. They cannot see. So they cannot see and they cannot attract. This is a simple way. But physicists say no. The gravity gets confused. Is it human mind to get confused? Is a force a human mind to get confused? No, it isn't. That's what we are working on. To prove that it is not human mind to get confused. There is one more thing. If there was no other stars, if the entire universe was filled with solar system, then what? If gravitational field extends up to infinity in all directions, then a star, which is the Cassiopeia or Betelgeuse, which is very big, and it does have gravitons, lot of gravitons surrounded for Betelgeuse, but when the sun and the Betelgeuse should attract, because the gravity extends up to infinity. But it doesn't. After some time, it vanishes all of a sudden. Nature is not like that. We need to have some explanation for it. And we are trying to find out that explanation. And gravity should actually decrease to zero. At 9.1 trillion miles, here it should be zero. It should not be 10. Go to some other distance and then find out. And again, after that point, you go to some other distance and again you find out. It's not the way it works. Right? So now, I'll actually discuss one of the problems that we actually found out in explaining how gravity cannot get confused. Okay, it's a simple explanation that we did. But say for example, this is sun, and this is sun. This is heliosphere. This is one ball. This is sun. Right? This is heliosphere. There is one more star. Okay, there is one more star which is say about 12 billion miles from sun. Okay, it's a small star. It's not a big star. Now it does have some gravitational influence. It's got its own sphere of influence and everything. So what happens if I place a planet here? You cannot literally do that, but what happens if I place a planet here? For example, these things happen in real life also. When an asteroid gets kicked out of Oort cloud or some asteroid belt that is present beyond the exoplanets, then this asteroid can wander between the two fields of gravity, right? So when it wanders between the two fields of gravity, then what? Where will it go? Which star will the asteroid be attracted to? Oh, you might say you're very intelligent. Whichever has got huge mass will attract towards that. Oh, no, it doesn't work that way. Sorry?
Then I'm not intelligent, I'm wrong.
No, that's not the way it works. We actually thought the same way and got rejected. So that's what, these are the basic problems that we are dealing with, and we hope to understand gravity better than what we understood during the times of Einstein's. But yeah, that's all. Thank you very much for listening to my lecture.
I don't know, what you are doing. You said I'm doing research or something.
Huh?
What are you doing?
The thing is, there's a lot of properties of graviton that people connected to chaos theories and all. They say if the field becomes zero, as I said, after some point of time, there will be some conditions in the space-time fabric that there will be a formation of black hole. It's rubbish, is it?
I don't know, I'm not intelligent.
Oh, come on. No, it is rubbish, is it? So, it doesn't explain how the nature works. We are trying to find out how exactly the nature works, rather than doing some equations and customs. Yeah. Actually, there are three people in our theory. One of the two students from University of Delhi and one student from local college in Ahmedabad is joining us. So we're working as a team, and we have a lot of mentors from Oxford and guiding us. No, I'm studying in Jaipur. Any other questions?
something which actually bothered me about theory of black holes provide. Information cannot travel faster than c, and gravity travels at the speed of c. So if the escape velocity is greater than c, how can gravity escape?
See,
From that
according to this theory, graviton being massless, it can travel close to speed of light. Okay? It cannot travel beyond speed of light. It is one of the fastest particles in nature after photon.
But so theoretically, if the escape velocity is greater than the speed of light,
But it doesn't work.
a graviton
Hawking
should
is
not
wrong.
be able to.
Hawking is wrong.
What?
Hawking is wrong. You know,
But
it's
black holes should exist.
well, it doesn't exist. Yes, one of the persons from Tata Institute is working on the same theory, and recently, probably 3 weeks back, Hawking also agreed to that. He said black holes doesn't exist. Okay, he has his own view of black holes. There is no singularity as such, but there is the event horizon, that is the radius of the black hole, beyond which whatever goes in, comes back.
I read somewhere recently, is gravity right-handed or left-handed? I didn't want to read that article, but independent. Just a couple of things, minor corrections if you like, in what was other an excellent lecture. You said the church killed Galileo, not literally. They put him under house arrest.
Yeah, but
It's like that maybe, but that's a philosophical question and we don't say
I
no
didn't want to
science.
say it.
Okay, secondly, the reason we didn't laugh at your, the reason I didn't laugh at your stone and apple and you
Yeah, and the angels.
You know, the angels is fine, I thought that was quite amusing. The apple part is totally apocryphal, you know that. Newton wrote that in his memoirs at the end of his life. He suddenly decided to concoct a story about the apple falling near his head. So that never happened.
No.
Okay, that's it. Many people don't know that. Then you probably said inadvertently, but you said that Copernicus proved Galileo's theory. That obviously couldn't happen because Copernicus lived before Galileo.
No, Copernicus.
Copernicus
Obviously after Galileo.
Copernicus died in 1543, Galileo.
Yeah, but his paper was published after Galileo.
No. Yes, 1543 is when Copernicus published his book, The Revolutionary Bus something something. The story goes that he got a copy of his book in his deathbed and he died seeing it. Galileo came up with his hypothesis 60 years later. Okay.
Are we talking about Galileo or Galileo Galilei?
Yes. Of Tuscany.
Sorry?
Galileo, yes. There's only one Galileo Galilei.
Yeah, fine.
Two other things. You mentioned, I'm sorry to be nitpicking, but I'm a nitpicker, okay? You said Einstein was 90, he was 26 actually, when he came out with the theory of relativity.
There is general, special
Special was the 27th of the 4 papers at University of Zurich.
Yeah. So he was born in 1879, 1905 is when he published his theory. And you're right, he was sitting in a tram and going towards the patent office in Bern when he came up with this theory. Okay, and one last really dumb question from me. G is 6.67 into 10 raised to
minus 11. Minus 11.
minus 45. What is the G which is 9.8 meters per second per second?
Sorry. See, what actually Galileo did, he went to the Leaning Tower of Pisa. He dropped two identical balls, and it fell towards the ground and simultaneously. And what he found out was, after 1 second of its motion, this is 1 second, the velocity of this ball will be 32 feet per second. Velocity. And the next second will be 64 feet per second. Okay? Which means that this ball, two identical balls, are accelerating towards the earth in Newton's sense, to be honest, or in the sense that we understand gravity, at a constant rate of about 9.78 meter per second squared, which happens to be something around 32 feet per second squared. This is the acceleration that every object accelerates towards the earth. Okay, and it varies height, position of where you are. Not much, but it does. So, yeah, this is how this acceleration is called as acceleration to the ground. Because what is accelerating? Because the gravitational force of Earth.
Is there a relationship between this small g and the big G?
Yeah, you can relate it. I have a formula. You know, when Cavendish did that experiment, he used the formula to actually find out the capital G. You can refer that book. It's very, very interesting. And I read it, I got goosebumps. You can read that experiment. To be honest, I never got goosebumps other than the theory, any other theory.
So can you explain dark energy with the gravitons?
Sorry?
Dark energy with the gravitons?
Dark energy, I can relate it with Higgs field, how the stars get mass, but I cannot relate it to dark energy. Dark energy is something that's very different. Dark energy is made up of two types of things that we think it is made up. We don't know. Okay? They are called as WIMPs, weakly interacting massive particles, or MACOs, okay? Massively compact hollow object. So either way, either of it goes straight through us without any interaction. That is what dark matter is. As of now, I don't know much. So yeah, graviton. Anything else?
Okay, there are no more questions. Thank you, Sanjay, very much for a very, very interesting talk. And he's spoken extempo, and that shows he's got quite a good control over the topic. And let's hear him more and more and about his field of experiment, research, whatever he's doing. And we'll wish him all the best in his further endeavors. Right? Thank you very much.